Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be doing more topical past paper questions for Cambridge A-level physics, and these questions come from the Papa Cambridge website, and we are still doing the topic of quantum physics. Now in the last video we did some questions at the beginning of the set of questions from Papa Cambridge that were mostly focused on the photoelectric effect. And today we'll do questions 356 to 364 as they are numbered on the document, which I will place in the description of the video so you can download this paper and work through these questions before you watch this video, and then use this video as a sort of a guide to see what you did right and what you did wrong. And these questions will be more on the topics of the de Broglie wavelength and energy levels in atoms and line spectra and absorption spectra and things like that, which we didn't get to in the previous video. So the first question here I'm looking at is question as it's numbered in the Papa Cambridge questions 356, and this is subject code 9702, which is physics. This is from summer 2019, which is May-June, and this is question paper 4, variant 2, and question 11 from that paper. And the first thing, as we've seen often enough already, is them asking us to state what is meant by a photon. Now we can use two words to describe how we would, or to state how we would describe a photon. It is either a packet or a quantum of energy. I think quantum is a word, or we can use packet or quantum, either one is accepted. But quantum is a more formal word. A quantum, a discrete amount of energy. And specifically, when that energy is in the form of electromagnetic radiation. So it's a quantum or a packet of energy in the form of electromagnetic radiation. And this is how we would describe what a photon is. It's a quantum of energy in the form of electromagnetic radiation. Now that's usually the startup question, and then followed by a more in-depth question. We're told that a stationary cobalt-60 nucleus emits a gamma-ray photon of energy 1.18 mega-electron volts. And the first thing we are asked to do is calculate the wavelength of this photon. Well, we know energy and wavelength are related. So energy is hc over wavelength lambda, where h is Planck's constant and c is the speed of electromagnetic radiation, which means I can rearrange this and find the wavelength lambda. And this you would have done a million times, and it's not really going to trouble you. So lambda is hc over E, which is Planck's constant. You go to your data sheet, find all of these values. 6.63 times 10 to the minus 34 joule seconds times the speed of light, 3.00 times 10 to the 8 meters per second, divided by the energy. Now the wavelength I want in SI units meters, so I have to convert the energy from mega electron volts to joules. So I have to go from mega to electron volts, multiply by 10 to the power 6, and then get rid of the electron volts, so I have to multiply this by 1.6 times 10 to the minus 19. And what I get is a wavelength 1.05 times 10 to the minus 12 meters. And since I'm given everything in three significant figures, I can keep it in my final answer in three significant figures. 1.05 times 10 to the minus 12 meters, a very short wavelength photon. And hence it's a gamma ray, short wavelength, high frequency. Now that we have the wavelength of the photon, we are asked to show that the momentum of the photon is 6.3 times 10 to the minus 22 Newton seconds. Now how do we show the wavelength of the momentum of a photon? We know momentum of a photon is E by c. And E, we said from above, is hc over lambda. So that's hc over lambda c. Well, guess what? This simplifies to h over lambda. H is a constant, Planck's constant, 6.63 times 10 to the minus 34. And luckily, we've already calculated the wavelength, 1.05 times 10 to the minus 12 meters. And what we find is that we'll get the value that they've asked us to find, 6.3 times 10 to the minus 22 Newton seconds. And so that value correlates with what we were asked to find. So that's the momentum of this gamma ray photon. Next, we are asked to use the information in B2 to determine the recoil speed of the cobalt nucleus when the gamma ray is emitted. So initially, what did they tell us? They told us that the cobalt nucleus is stationary. So cobalt is stationary, sitting on its own. It suddenly and spontaneously emits a gamma ray photon, and it recoils backward. Now, what do we know? That the momentum before the cobalt emits the gamma ray is 0. So the momentum after it emits the gamma ray must be 0 as well, which means it must have the same momentum as the gamma ray photon, but in the opposite direction. And so since momentum is a vector, the two momenta will cancel and the final momentum is 0. So the momentum of the cobalt nucleus is m delta v, which is m times its final speed, since its initial speed is 0. It starts from rest. So the speed that the cobalt nucleus recoils with is its momentum divided by its mass, a little bit of rearranging, p over m. And its momentum, like we said, must be the same as that of the gamma ray photon that's emitted, which is 6.3 times 10 to the minus 22 Newton seconds. So even if you didn't calculate it above successfully, you could still use the value that they told you to and do this calculation. We divide that by the mass of the cobalt nucleus. Now the cobalt nucleus, it's cobalt 60, so it has 60 nucleons, times the mass of a single nucleon, which is the atomic mass unit, 1.66 times 10 to the minus 27 kg. And so if we do this calculation, what we get is 6.33 times 10 to the power 3 meters per second. So even though cobalt is quite heavy, it has a significant recoil speed, 6,300 meters per second. Two significant figures, that's 6.3 times 10 to the power 3 meters per second. And so always remember that if a nucleus is stationary and suddenly and randomly emits a photon, the nucleus will recoil, and its momentum will have to be equal and opposite to the momentum of the photon that's released in order to conserve momentum before and after. You can think of this as a cannon. A cannon firing a cannonball will initially have a momentum of 0, and after firing the cannonball moves in one direction and the cannon moves in the other direction, and they must both have the same momentum in opposite directions so that the final momentum is still 0. And so this is sort of analogous to that situation. And so the next question we will look at is question 357. This is again 9702. This is from winter 2017, which is November-December, question paper 4 variant 1, and this is question 11 from that paper. So again, they ask us to state what is meant by a photon. You can see that this is probably going to be a very common type of question. So being a lazy physicist, I'm going to copy and paste that because by now you memorize this to the T. What is meant by a photon? It is a packet or a quantum of energy that is in the form of electromagnetic radiation. The number of marks may vary, but I don't think that your answer to this question should necessarily vary. I think this is the most basic but best answer to give to what is meant by a photon. For B, we are told that indium-123 is radioactive. A nucleus of indium-123 emits a gamma ray photon of energy 1.1 mega electron volts. Determine for this gamma radiation the frequency. Again, this is something that we do in our sleep. E is HF. I know the energy. I know H is a constant. I can find the frequency. So the frequency of this gamma ray photon is E by H. And this is 1.1 times 10 to the power 6 to give me electron volts, and then times 1.6 times 10 to the minus 19 to give me joules. Why do I want joules? Because the frequency is in SI units of hertz. and I divide this by Planck's constant 6.63 times 10 to the minus 34. And so what I should get is 2.65 times 10 to the power 20 hertz, very high frequency wave, very high frequency photon, I should say. And that's 2.7 times 10 to the power 20 hertz. And so that's the frequency of this gamma radiation. Next, they ask us for the momentum. Well, the momentum, we know that lambda is h over p. I'm just stealing this from the previous question. And therefore, p is h over lambda. But I don't have the wavelength, I do have the frequency, so I can write this as hf over c. Remember, lambda is c over f. And so this I can write as (2.65). Actually, let's put Planck's constant first to stick with the convention, the order rather. So 6.63 times 10 to the minus 34 joule seconds times the frequency 2.65 times 10 to the power 20 divided by c, which is 3 times 10 to the power 8 meters per second. And what I get is the momentum of the photon p to be 5.86 times 10 to the minus 22 Newton seconds, or to two significant figures, 5.9 times 10 to the minus 22 Newton seconds. So you can see the momentum of a single photon is quite insignificant. But remember, photons rarely come isolated, they come in large numbers. So photons in collective can have a significant momentum. Next, we are told that the indium-123 nucleus is stationary before emission of the gamma ray photon. Use your answer in B2 to estimate the recoil speed of the nucleus after emission of the photon. Just like the previous question, what does this tell us? The indium nucleus is stationary before the emission of gamma ray photon. That means after it emits the photon, it must recoil backward and have the same momentum as the photon. Why? Because the momentum of the photon and the momentum of the nucleus recoiling must have a total momentum of 0, since before emitting the gamma ray photon, the stationary indium nucleus had a 0 momentum, it wasn't moving. So momentum is m times v. This is from AS physics, which means that the speed, v, is the momentum of the nucleus divided by its mass, which is the same as the momentum of the emitted photon, 5.9 times 10 to the minus 22 divided by, now the mass of indium-123 is 123 nucleons times the mass of a nucleon, 1.66 times 10 to the minus 27 kg, which is the atomic mass unit. And what we get is another very high value, obviously less than what we got for cobalt in the previous question, 2.89 times 10 to the power 3 meters per second, or 2.9 times 10 to the power 3 meters per second. It's lower than the value we got for cobalt-60 in the previous question because cobalt was lighter. Indium is much heavier, so it will still recoil with a significant speed, but not as quickly as something that's lighter, obviously. And so that would be the final answer. That question was worth 7 marks. The next question is question 358. And see, so far we haven't really had anything that tested us too much, which is good in a way, I guess. But it's also good to get the difficult questions attended to. This is from Winter 2017, and this is question paper 4, variant 2, question 10 from that paper. And we're told that a metal surface is illuminated with a light of single wavelength lambda. On the figure below, on figure 10.1, sketch the variation with lambda of the maximum kinetic energy Emax of the electrons emitted from the surface. And on your graph, mark with the symbol lambda naught the threshold wavelength. So we need to sketch a graph of Emax against lambda. So this is the photoelectric effect, and the first thing I need to do is figure out what this graph would look like. So I'm going to write the photoelectric equation out. Hc over lambda, the energy of the incoming photon, is equal to the energy of the outgoing electrons E max plus the energy required to get the electron out of the metal, which is the work function energy phi. So I'm going to rearrange this so that E will be alone on the left-hand side. Hence, we can plot that on the y-axis. And E max is Hc over lambda minus phi. Now, if you ask me to plot a graph of E max against 1 over lambda, I'd be quite happy because I'd have a straight line graph with gradient Hc and y-intercept minus phi. But I'm plotting a graph of E max against lambda. So it's not going to be a straight line. In fact, you can see that this is going to be a hyperbola. Y is equal to something over x minus c, whatever, minus a constant. So this is in the form of a hyperbola, and it's going to have two asymptotes. One asymptote will be the y-axis, the E max, and the second asymptote will be the work function of the metal. So what I need to do is draw this, well, sketch this hyperbola. I don't have values, so I don't really need to draw it in any specific size, but it needs to look hyperbolic in shape. It needs to have a concave curvature, and it needs to always have a negative gradient. And so it has a very steep gradient, and then the gradient slowly decreases, but always remains negative. And obviously, with you drawing this with pencil, it would be a lot easier. But the graph does cut the x-axis, and the point at which it cuts the x-axis, the lambda axis, that point we will label as lambda naught. That was asked specifically of us to mark the value of the threshold wavelength. The threshold wavelength occurs when there is no kinetic energy, when E max is equal to 0, and hence that's the x-intercept. So again, it would look a lot better if I did this with pencil, but that's the shape of your graph. Don't be confused into thinking that this graph will not cut the x-axis. It will, because it's shifted down by phi units, where phi is the work function energy. And so we get a nice hyperbola. The next question says a neutron is moving in a straight line with momentum p. The de Broglie wavelength associated with this neutron is lambda, and on figure 10.2, sketch the variation with the momentum p of the de Broglie wavelength lambda. It's kind of like they're trying to show us a pattern, some similarity. What we know is lambda is related to p by lambda is equal to h over p. But if I'm plotting a graph of lambda against p, what do I get? Guess what? I get another hyperbola. But in this case, the asymptotes are the lambda axis and the p-axis, the y and the x-axis. So I will get a irregular hyperbola, and I now have to make sure that my graph is hyperbolic, but also does not touch either axis. And again, it's a sketch graph, so there's no values required, but the shape needs to be this concave shape with the gradient always negative and always decreasing. And so this is what my hyperbola looks like. So there's a pattern, after all, between these two graphs. They are both hyperbolic in shape. So kind of proves a point. Now, you wouldn't normally think to plot a graph of E versus lambda for photoelectric effect, but you can see why maybe plotting graphs of equations that you run across when studying physics might be a good idea, so that if you encounter them at a later stage, it doesn't take you by surprise. But anyway, with a basic knowledge of mathematics, you can see that it's not too difficult, and it's well, I wouldn't say a quick 5 marks, but not a difficult 5 marks to score. And that was the entire question, just drawing those two graphs. So a shorter question there. Now the next question is, well, it's question, I looked at the first question and I'm like, okay, here we go again. Anyway, this is question 360 as numbered in Papa Cambridge in the worksheet. This is from winter of 2018 and from question paper 4, variant 2. And this is question 11 in that paper. So again, if you want to find these individual questions, you're more than welcome to do that. But guess what the first question is? State what is meant by a photon. It seems like this question is quite popular. So again, being lazy, I'm going to copy that and paste it in. But unfortunately, you can't do this in an exam, so you have to write it down. It is a packet or quantum of energy in the form of electromagnetic radiation. Next, we are told to describe the appearance of a visible line emission spectrum as seen using a diffraction grating. So I need to read this question. I'm asked to describe something. That's my question word. But I'm asked specifically to describe the appearance of a line emission spectrum, specifically visible, things that I can see. So visible, I should underline the word visible as well. So I'm not asked how the line emission spectrum occurs. I'm not asked to explain energy levels, etc. I'm asked to explain what it looks like, which is a lot easier because then I just think back to, I get my memory to go back to my textbook and I think of the lines in the textbook and I describe what I see. What do I think of when I think of a line spectrum? Well, a line spectrum consists of colored lines on a dark background. So I'm going to say colored lines of specific, I'm actually just repeating myself here, but of specific wavelengths that are set against a dark background. So if you think about the emission spectrum of hydrogen, for example, I have a dark background and a few lines, red, blue, green, violet, whatever. And so it consists of colored lines of specific wavelengths set against a dark background. Again, I'm only asked to describe the appearance, not describe how the lines are formed. The next question tells me that the lowest electron energy levels in an isolated hydrogen atom are shown in the figure. And an electron is initially at the energy level minus 0.85 electron volts. State the total number of different wavelengths that may be emitted as the electron de-excites. Okay, so how many different wavelengths can be emitted by this electron? So this electron is at that energy level there. If we call the first one E1, then the electron is at E4, the fourth energy level. So the electron can go from E4 to E3, energy level 3, which is the one just below it. It can go from, as long as an incoming photon has the energy equal to that gap between levels, or if the electron were to jump down rather between two energy levels, it will emit a photon. And it will be excited to that level again if it absorbs a photon with energy equal to the difference between levels. So it can go anywhere. It can go from E4 straight to E3, E4 straight to E2. Any of these are permitted transitions. The electron can move in any way. Or E4 straight to E1. Those are 3, but those are not all. I mean, what if it starts at 3? What if it goes from E4 to E3 and then from E3 down to E2? Or from E3 down to the ground level, minus 13.6 electron volts, E1. All of these are going to give us different, the gaps of energy are different, and so the wavelengths of the photons that are produced when the electron does this is going to be different. And the last one could be from E2, starting at E2 and ending at E1. So what I will do actually is draw these lines. Might be a good idea for me to draw these lines. So I'm going to go E4. I think it might be a better idea if I physically draw them. So I said E4 to E3, and then E4 to E2, and then E4 to E1. The length of these lines are different, the energies are different, so the wavelengths of the photons produced are different. Then I go from E3 to E2, and E3 straight to E1. And lastly, the last remaining jump is going straight from E2 to ground state energy E1. And so altogether, I see there are 6, what should I call them, de-excitations. The opposite of an excitation is a de-excitation. And so the number of wavelengths that may be emitted as the electron de-excites is 6. 6 different photons can be produced if the electron's initial position was 0.85. You can see that if the electron jumps up a level, there'd be even more jumps that can occur and even more wavelengths that can be released. So a single hydrogen atom can give rise to many different colored lines. Some of them may be visible, some may be not visible. We are told then that photons resulting from electron de-excitation from the minus 0.85 energy level are incident on the surface of a sample of platinum. And platinum has a work function of 5.6 electron volts. We want to determine the maximum kinetic energy in electron volts of a photoelectron emitted from the surface of platinum. So I'm suddenly given this information and told to find the energy of a photon if it was excited by the energy of an electron rather that is emitted from the surface when an electron de-excites from the minus 0.85 electron volt energy level, giving off a photon. Well, that's a lot of information. Before I even get caught up with what I need to do, let me just write down the equation of the photoelectric effect. The energy of the photon is equal to the energy of the electron, we usually call it E max, plus the work function energy, phi. What this means is the maximum energy of the emitted electrons is equal to the energy of the photon minus the work function phi. But wait a minute, the energy of the photon is the photon that's released when the electron jumps from the minus 0.85 energy level and jumps to the ground state. Now, why am I saying ground state? Why am I saying that the electron is doing this jump, the one that I'm highlighting, from 0.85, from negative 0.85 to negative 13.6? I'm saying that because the question says, what is the maximum kinetic energy that a photoelectron can have? So if the energy is the maximum, the energy of the photon that's being produced when the electron de-excites needs to be a maximum. And so I have to have the biggest jump in energy. Hence I'm using 13.6 minus 0.85. I'm ignoring the negatives because it turns out to be the same thing, minus the work function, which is given to be 5.6 electron volts, and what I get is 7.15 electron volts. The question requires me to answer in electron volts, so to two significant figures, this is 7.2 electron volts. So that's how we go about thinking about that. The biggest energy photon will come from the biggest de-excitation of the electron. Now the wavelength, we asked now to determine the wavelength of the photon produced or producing the photoelectron in part 1. So what do we know? We know the energy of a photon is related to its wavelength, hc over lambda, which again means that we can find the wavelength of the photon as hc divided by its energy. And again, putting our values in, this is 6.63 times 10 to the minus 34, Planck's constant, times c, which is 3 times 10 to the power 8, divided by the energy of the photon, which is 13.6 minus 0.85. And we have to multiply this by 1.6 times 10 to the minus 19 to get our energy in joules and hence our wavelength in meters. And what we get is the wavelength of the photon that produces this photoelectron is 9.75 times 10 to the minus 8 meters, or 9.8 times 10 to the minus 8 meters. So that question had a good mix of a little bit of conceptual understanding and then the energy level diagram for hydrogen, which I know is troublesome for many of us. But again, all I need to remember is that when an electron jumps down, out comes a photon. If a photon comes in, an electron will absorb it if the energy of the photon is exactly equal to the difference between two energy levels. And so that simple idea can be expanded to ask questions such as these. And this was a longish type of question, 10 marks in total. Now the next question is somewhat of a nightmare for many of you. We'll try to demystify it. It's question 361. And this is from summer 2017. Summer being May, June, question paper 4, variant 1, and this is question 11 from that paper. So we are told that a beam of light consists of a continuous range of wavelengths from 420 nanometers to 740 nanometers. That's Roy G. Biv. That's the violet all the way to the red end of the spectrum, so visible light. The light passes through a cloud of cool gas, as shown in the figure. And the spectrum of light emerging from the cloud of cool gas is viewed using a diffraction grating. So basically, we, like passing light through a prism, we allow the light to diffract, and then we look at the specific colors that come out. And what we find is we see a number of dark lines set against a colorful background. And we want to know why, we want to explain why the spectrum contains a number of dark lines. So basically, all they're really asking you to explain here is why an absorption spectrum is a thing. Where does the absorption spectrum come from? Essentially, that's what they're asking. This is a cool gas, the atmosphere of a star or a planet. White light exiting that star gets absorbed by the atmosphere, and what we get is, instead of seeing a nice continuous spectrum, we know that white light is made of all the colors, we see all the colors minus very specific lines. So why does this happen? So the incident light, the white light coming from the star, I'm using the star as an example, so this can link to cosmology. So what happens is the incident photons are absorbed by electrons. And when I say incident photons, I mean the photons of a very specific wavelength. So if the gas is hydrogen, it is in this case, but if the gas is hydrogen, they didn't say hydrogen, did they? Well, if the gas is hydrogen, then what we get is the line spectrum for hydrogen. Those would be the energy level differences. Those will be the energies of photons absorbed by the electrons in the gas. The electrons get excited and they go to a higher energy level because they've absorbed the photons. But the electrons, just like you, when you're very excited, want to de-excite. So the electrons then, actually before we even get there, the electrons are now excited, one step at a time. The electrons are excited and move to higher energy levels. Now the difference in the electron energy levels is equal to the photon energy, so the energy of the photons that were absorbed. So that doesn't explain why we have dark lines. So in comes photons, absorbed by the electrons. The electrons go up an energy level. What happens next? The electrons then de-excite. So just like you, after you have coffee, you want to de-excite. The electrons want to de-excite themselves, and so they emit photons. And they emit exactly the same photons that they absorbed in the first place. Now, the reason why they're dark lines is because the emitted photons are in all directions. Whereas the light that was incident on the cool gas was in one direction, the photons that are absorbed by the gas, not the other ones that pass straight through, but the photons that are specifically absorbed will be emitted in all directions. If they're emitted in all directions, what we see is that their intensity appears lower. So they appear dark, whereas everything else appears bright. And so that's where we get the dark lines in an absorption spectrum. So the incident photons are absorbed by electrons in the gas. The electrons increase in energy level. and the energy level increase will be dependent on the energy of the incoming photons, the electrons will de-excite, emitting all the same photons that they absorbed, but it will emit them in all different directions. So when we look at the light coming from the gas, from the star, for example, we'll see the continuous white spectrum, things that weren't absorbed, and the things that were absorbed will come to us, but with a lower intensity. They'll appear dimmer because the light's been fired off in all different directions. And those are the dark lines that we see. So that explains the absorption spectrum, but also answers this question. Now, it's important that you know that because that's a 4-mark question, so it's not something you want to miss out in a test or an exam. In part B, we are told that some of the electron energy levels of the atoms in the cloud of gas are represented in the figure. It turns out this is the hydrogen atom. They don't tell us, so we'll just assume we don't know what it is. And in this figure, we are then told that light of wavelength 420 nanometers has a photon energy of 2.96 electron volts. Calculate the photon energy of light of wavelength 740 nanometers. Okay, so energy is hc over lambda. For once, we can just simply calculate the energy rather than rearranging and solving for something else. This is Planck's constant 6.63 times 10 to the minus 34 times 3 times 10 to the power 8 divided by the wavelength of this light, 740 times 10 to the minus 9 meters, 740 nanometers, and I have to convert this to electron volts, so I must divide my entire answer by 1.6 times 10 to the minus 19 joules per electron volt. And what I get is 1.68 eV, electron volts, or 1.7 electron volts. And so that's the photon energy if the wavelength is 740 nanometers. So you can kind of see now why we use electron volts rather than using joules all the time. Much easier to write. Now we are told that we need to use the data from part 1 and our answer in part 1 to show on the figure the changes in energy levels giving rise to the dark lines. So I need to know which ones of these transitions are going to give rise to the dark lines. And remember, the light that's passing through the gas is between 420 and 740 nanometers. So only energies in between 420 and 740 nanometers are going to be absorbed. So what this means is that my energies must be between, my photon energies and hence electron transitions must be between 1.68 and 2.96, which is given in the question. The one I've calculated, 1.68 and 2.96 electron volts. And so I need to look for all the transitions where the change in energy level, the difference between energy levels, is between these two values. Now again, I can go and do every single one and figure out what those change in energy levels are, but I can sort of identify that just by looking. So 1.7 to 2.96, let's say 1.7 to 3. I know that 13.6 minus any of these values above is going to be much greater. So I know that the last energy level is not going to be the ground state energy level. But what I can see is that if I take 3.4 and I subtract 0.54, what I do get is a jump that's still less than 2.96. So it turns out that the first jump will be from 0.54, an electron de-excitation, or you can draw the arrow the other way, it doesn't really matter in this case, to 3.4. And obviously I need smaller energies than that. So I need to then do the next jump. And it turns out the only other one that's smaller but will still allow this to hold, that condition to hold, would be the jump from 1.5 or minus 1.5 to minus 3.4 electron volts. So I actually need 3 lines, and I'm going to get 3, that means I'm only going to get 3 dark lines in my absorption spectrum if I look at only the visible part of the absorption spectrum. So I'm looking with my eyes obviously, and only picking up those visible colors. And so I'll have 3 lines, and again, it doesn't really matter in which direction you draw the arrows, because remember, electrons are exciting and de-exciting in this entire process. And so that's what you would do. That's how you would draw changes in energy levels considering the lines in the spectrum. So the lines in the spectrum, the colors in the spectrum, all, remember, each one of these lines is a specific photon. So I'm exaggerating a bit, but the smaller energies will be your long wavelength, short frequency, or low frequency red light, and then your bigger jumps will be your more blue or purple, high frequency, short wavelength photons. And so that's how the colors in the line spectrum, or in the absorption spectrum in this case relate to energy levels in atoms. So a little crash course there. Now the next question is question 362, as numbered here, and this is from summer 2017, May-June, question paper 4, variant 2, and question 11 from that paper. Now the first question is quite different. We're told that an electron has charge minus q and mass m. It's accelerated from rest in a vacuum through a potential difference v. Show that the momentum of the electron is square root of 2mqv. Well, this is an interesting one. I've never seen this expression before, so I have to do a little bit of thinking. Now what I know is the energy given to the electron is q times v. Told its charge is q, its potential difference is v. So the energy given is qv, positive qv. But the electron will gain a potential, will convert this potential energy to kinetic energy as it starts to accelerate. And so its final kinetic energy is a half mv squared. That's Ek. So what does this mean? That means I can write an expression for little v in terms of big V. So the speed v is, if I rearrange this, the square root of 2q big V over m. Well, that in itself doesn't look anything like what I'm asked to prove, but I also know that the definition of momentum is mass times velocity, m times v. And so I can write this as m multiplied by my new expression, 2q big V over m. And I can make this a lot neater. I can take the m into the square root sign by writing it as m squared. Square root of m squared is simply m. So I can bring everything under the square root side, inside the square root sign, and I can write this as square root of 2m squared q big V over m, which lo and behold gives me the expression I've been asked to find, the square root of 2mq big V. And so I didn't know how to find the momentum, but what I did was took the information that I had, found the kinetic energy, and found an expression for V, which I could then use in the regular expression for momentum. So always take the things that you know and put all the information together to try and derive an equation that you may have never seen before. So a little bit of mathematics there. We are then told that the potential difference V through which the electron is accelerated is 120 volts. And we are first asked to state what is meant by the de Broglie wavelength. Now, what is the de Broglie wavelength? Now, state what is meant by it is, what does it mean when I say something has a de Broglie wavelength? So it is a wavelength, or it is the wavelength that is associated with a particle in motion. Simple, actually. So I can also say the wavelength associated with a particle that is due to its motion. So things that are classically particles, things with a mass, electrons, protons, tennis balls, whatever, etc. When they move, they have an associated wavelength, and that is due to its motion. So that's what de Broglie's wavelength basically says. It's the wavelength of anything that's a particle because it's moving. Simple, straightforward, but that's sort of the statement of what we understand by de Broglie's wavelength. And you can understand what's coming next. They ask us to calculate the de Broglie wavelength of the electron. Now, the equation for de Broglie wavelength, lambda is h over p. I don't have the momentum, but I have an expression for the momentum, and I'm given the potential difference through which the electron is accelerated. Now I know the purpose for the derivation. That's h over the square root of 2m cubed big V. Planck's constant 6.63 times 10 to the minus 34 divided by the square root, remember the square is only in the denominator, 2 times, and be careful, this is the mass of an electron, 9.11 times 10 to the minus 31, times the charge of an electron, which we know is 1.6 times 10 to the minus 19, and the potential difference through which it's accelerated is 120 volts. Putting this all in my calculator, I get this to be 1.12 times 10 to the minus 10 meters. What are two significant figures? 1.1 times 10 to the minus 10 meters. So I can find the de Broglie wavelength because I was given an expression where the mass, charge, and voltage were all known. Next, we are told that the separation of copper atoms in a copper crystal is 2 times 10 to the minus 10 meters. Now, by reference to your answer in B2 suggests whether electron diffraction could be observed using a beam of electrons that have been accelerated through a potential difference of 120 volts and are then incident on a thin copper crystal. So they want to know if I take these electrons that I'm using, accelerating through 120 volts, and I fire them at a copper crystal, if they will diffract. And they have a space to diffract of 2 times 10 to the minus 2 meters. Now what I can see is that 2 times 10 to the minus 10 meters is on the same order of magnitude as the wavelength of the electrons when they are accelerated through 120 volts. They're not the same value, but they do have the same order of magnitude, 10 to the power minus 10. And so what do we know? If waves have roughly the same wavelength as the gap through which they are moving, they will diffract. And so electrons will diffract. And so I can say that the wavelength of the beam of electrons, is on the same order of magnitude, so roughly the same size as the separation of copper atoms, and so diffraction will be observed. So we can use 120 volts, electrons accelerated at 120 volts to undergo electron diffraction and hence determine things about this crystal. So diffraction will be observed. So always look at the order of magnitude of the wavelength of the electrons and the size of the crystal, and if they're in the same order of magnitude, then we can say that yes, diffraction will occur. And that's a 2-mark question to finish off the 9 marks for this question. So this one's a little bit tricky. It was a bit of mathematics and some conceptual understanding about crystal diffraction. So you need to know electron diffraction. It's an important observation when we think of how particles can behave like waves, not just how waves can behave as particles, as the photoelectric effect showed us. Now the next question is question number 364, as numbered in the document. This is question 364. This subject code 9702. This is from winter of 2016. Question paper 4, variant 2, and this is question number 12 from that paper. So the first question says, state an effect, one in each case, that provides evidence for the wave nature of a particle. So things that were classically thought as particles. Is there any effect that shows that these actually have a wave nature? Well, we've just described one. Electron diffraction. Or you can say the electron microscope is another accepted answer. But electron diffraction is when electrons, which were traditionally thought as particles, undergo diffraction, which is a wave property of motion. And so electrons can exhibit wave natures, even though we always have assumed them to be particles. On the other hand, can we state an effect that provides evidence for the particulate nature of electromagnetic radiation? Well, I just mentioned one, the photoelectric effect. The photoelectric effect is one, Compton scattering could be another one. But we'll just stick to the things that we've already studied. So the photoelectric effect is where light, which is previously thought to be a wave, behaves as a particle, as Einstein showed. And so there's, just as waves, traditional waves can behave as particles, traditional particles can behave as waves. So it's very difficult to separate the two. We're then given 4 electron energy levels in an isolated atom, shown in the figure. And we are told, for the emission spectrum associated with these energy levels, to mark with an arrow specifically, the transition that gives rise to the shortest wavelength. So an electron is somewhere here, it jumps down and gives rise to the shortest wavelength. So how do I know that? Well, let's look at the energy first. Energy is proportional to frequency. But frequency is inversely proportional to wavelength. So the energy is inversely proportional to wavelength, which we kind of know. Longer wavelength, lower energy. Shorter wavelength, like X-rays and gamma rays, higher energy. So if I want the shortest wavelength, I want the biggest energy. And the biggest energy jump will come from, well, the biggest jump, physically, visibly. And that's from the minus 0.54 electron volt energy level all the way down to the minus 3.4 electron volt energy level. And this jump is the biggest change in energies, hence the biggest energy given to the photon that will be emitted when the electron does this jump. And we are then told to show that the wavelength of this transition is 4.35 times 10 to the minus 7 meters. So what we know is the change in the energy, delta E, is hc over lambda, the energy of the photon that is emitted. And so lambda, the wavelength of the photon, is hc over delta E, which is 6.63 times 10 to the minus 34 joule seconds, that's Planck's constant, multiplied by the speed of the electromagnetic wave, 3 times 10 to the 8 meters per second, divided by the change or the difference in energy levels. So 3.4 minus 0.54, but that's in electron volts, so I need to multiply this by 1.6 times 10 to the minus 19 joules per electron volt. And what I get is, just as the question asks, 4.35 times 10 to the minus 7 meters. And so I get the wavelength of the shortest transition, which is violet to blue light, the lower end in the wavelength of the visible spectrum. And so this is a question that tests a little bit of our the concept knowledge, but also there's some mathematics involved. And weirdly, we are asked later on the question, which seems to be like a recurring theme, later in the question we are asked to state what is meant by the de Broglie wavelength. And once again, I'm not going to do it because I've done it before. So the de Broglie wavelength is the wavelength of any particle due to its motion, or the wavelength associated with a particle in motion, or the wavelength associated with a moving particle. Anything to that order, to that degree. And in the last question, we are asked to calculate the speed of an electron having a de Broglie wavelength equal to the wavelength in B2. So they're saying, hey, here's a photon with this wavelength. how much energy would, or how much speed would an electron need to have in order to have the same wavelength? Well, what I know is that lambda, the de Broglie wavelength, is h over the momentum of the particle, which we know as mv, which means the speed of the particle, v, is h over m lambda. Remember now, this is an electron, it's a particle, has a mass. So that's 6.63 times 10 to the minus 34 Planck's constant divided by the mass of an electron. Remember, this is in your data sheet, so you should be able to read this off without getting it wrong. 9.11 times 10 to the minus 31 kgs. And let's assume it had a wavelength of 4.35 times 10 to the minus 7 meters. And this is a very high speed indeed, 1.67 times 10 to the power 3 meters per second. Not impossible, but still a very high speed. 1,670 meters per second will be required by the electron if it were to have the same wavelength as a violet blue photon. And so this question in total was 9 marks. And it was a question that linked concepts and theory to mathematics, but again, these last few topics, like I said before, they are very heavy in conceptual understanding. And you could have 4 or 5 mark questions that ask you to explain a concept in detail, including all its important points. So I think this covers quantum physics fairly well, and we'll stop there for this video. And I'll keep uploading videos, doing topical past paper questions on different topics, trying to get as much done before the exam. But make sure to use these questions if you're lacking motivation or lacking a definite source of material that you need to study with. And that's all from me, Mr. K, for now. I'll see you again next time on Everything is Relative.